Hi, chemistry students. Let's talk about salts, and especially these hydrolysis reactions where the salt is going to somehow interact with water to form some products. And it's this reaction which is responsible for salts having the properties discussed in the first video about the qualitative aspects of salts in water. So when you get to the point where you're trying to figure out how to do a problem that might involve a salt, you have to be able to identify whether the substance you're talking about is an acid, a base, a salt, or possibly none of those. So I've put a few compounds here together for you to take a look at, and I'd like you to stop the video and just look at them and see if you can figure out which one's an acid, which ones are bases, which ones are salts, and which ones are not any of those three. So do that real quick. Okay, so hopefully you're back and you've given this a good old college try. So let's take a look. Calcium bromide, CaBr2. That's a metal and a non-metal. And those are our prototypical salts that we would ever see made from calcium hydroxide and hydrobromic acid. So when you see a metal and a non-metal, that's probably going to be a salt. Lithium hydroxide, well, in all honesty, it's a salt because it's an ionic compound. However, it's got other properties which dominate, which means it's got this hydroxide. That's a base, and we wouldn't consider that to be one of our salts. Next, we have CH3NH2, which is methylamine. And when you see these nitrogen compounds like these amines, look at the nitrogen and see how many things might be bonded to it. We've got the CH3 and two different hydrogens. That's three things bonded to this nitrogen, and nitrogen likes to make three bonds. So this is not some sort of ionic compound. This is just a covalently bonded compound that is a base. It's an amine. Now we look at NH4Cl, and once again we've got a nitrogen sitting there, but look what's bonded to it. 4 hydrogens. Because of that, that's an ammonium, and then it's got the Cl. You can see now that there's two different aspects to this particular substance. There's, on the right-hand side is this anion, this chloride, and on the left-hand side this ammonium. That's an ionic compound, and it's made from ammonia and hydrochloric acid. That right there is definitely 100% a salt. KNO2, it's the same kind of thing. It's got the potassium part from potassium hydroxide, and this NO2 from HNO2. That's definitely a salt. HClO2, well, it starts with a hydrogen. I hope you immediately said, oh, that's an acid, and it is. We then get to this C6H5NH3I. What a big mess that is. But take a look over here. You see this iodine? You don't see iodine in a lot of substances that aren't a salt. As a matter of fact, the only thing that's not really a salt in it would be something like HI. There are other classes where you'll learn more about iodine compounds. But for us, iodine really is, unless it's I2, is going to be part of a compound that isn't a salt. So this is definitely a salt, and it's going to be made of the C6H5NH3 plus and an I minus. So what about C6H6? Well, that's benzene, and benzene's not an acid, base, or a salt in this class. So just one of those things that does not belong here. That being said, what we're going to do is we're going to focus on what happens when we put each one of these into water. So I'm going to stop recording real quickly, erase this, and we'll just focus on these three and ask a different question. Okay, welcome back. And if you take a look here at our 4 salts that we had, the question that we want to ask now is, how in the world do these salts behave when we put them in water? So do they react with water? What's going on? And we're going to think about this as a 2-step process. The first step is salts they're going to first dissolve and dissociate. So by dissolve, once again, we mean that they're going to break apart into individual molecules or compounds or individual units. And then those units can further break apart into ions. So that's what this last part is. Just remember, this is making of the ions. And once that's completed, the ions will have the opportunity, they'll have a chance to react with water. And when they do this, they're going to be able to do, they're going to try to do this for one reason, and that is to make an equilibrium with their parent acid or base. So let's think about this before we even get started. If I take a look at just something like calcium bromide, calcium and the bromide right there, both of those parents, CaOH2 and HBr, are strong acids and bases, and neither of those make an equilibrium. So if I'm saying I'm going to try to make an equilibrium with my parent, calcium and bromine don't do that. So that's the beautiful thing about them. That's why this is a neutral salt. It's got this strong characteristic, but neither of those ions are going to try to make something in equilibrium because their parents don't make equilibrium. You'll see what that means a little bit better when we look at our next example, which is ammonium chloride. So with ammonium chloride, if I was to let this thing break apart, I would end up with NH4Cl. If I put that, maybe a solid of that, into water, then I would end up with some NH4 plus ions and some Cl minus ions. All right. The NH4 plus, if you remember correctly from when we first started looking at acids and bases, NH3 is its parent. And when NH3 reacts with water, it creates an equilibrium to form NH4 plus and OH minus. And you may also further remember that we called NH4 plus, we called it the conjugate acid. We did this because it's conjugate to the NH3 in the sense that one of these things cannot exist in water without the other. Now, and in general, there's not a lot of the NH4 plus around in this equilibrium, and we know that because of the small equilibrium constant for ammonia. But the key point is we cannot put ammonium into water without ammonium trying to make an equilibrium that includes NH3, ammonia itself. On the other hand, our friend chloride is from hydrochloric acid, and there is no equilibrium that it establishes with HCl, its parent, and therefore we can just kind of ignore it at this point as not being relevant to the problem. The problem is what happens when this stuff gets into water. So I'm going to move down here and scroll, but if we take a good look at this, we now have this in our solution is this ammonium, and it wants to somehow make an interaction with water that will allow it to be in equilibrium with NH3. To do so, there's only one thing it can do, and that is react with water itself. So this guy from right here can now react with water. Oop, that should be NH4 plus. And we just called it an acid. We said it's the conjugate acid of NH3. So as an acid, and it reacts with water, it's not a strong acid, so it's going to be in equilibrium. This acid's going to donate a proton to the water. And we're going to end up with our ammonia, NH3 aqueous, plus H3O plus aqueous. So now we can actually see why this is also called a conjugate acid. When it reacts with water in this process right here, which we've just done, which is called hydrolysis, that's not going to write out very well. Well, that process is called hydrolysis. In this process, we've seen that we've created the equilibrium again between these two substances. The difference being is that when ammonia dissociated into NH4+, it was acting as a base, but ammonium will act like an acid. Let's try this with one more of our examples with KNO2 and see what we get with that particular substance. So we're going to take KNO2. First thing we let it do is we say, let's imagine the solid is put in water. What's it going to do? If we do that, it's going to make K plus aqueous, and NO2 minus. How do I know that? Well, because this is the two ions that are here. We got a polyatomic ion on the right, which is the NO2 minus, and the potassium ion. This is a salt, and it's made of two ionic pieces. And we've got two then possible species that can react with water. I look at the potassium and I say, wait, that's from potassium hydroxide. The cation's a base, and this is from potassium hydroxide. And potassium hydroxide is a salt, or is a strong base. Therefore, I can just ignore it. I'm not gonna do anything with it. I don't recommend that you necessarily cross it off as I did, but I'm just trying to give you the idea that we're going to ignore it now because it doesn't make an equilibrium. It just floats around as potassium ions. All right. Well, the NO2 minus, though, is not from a strong acid. So its parent is HNO2. And HNO2 is not strong. That happens to be a weak acid with the equilibrium constant, I think, of about 10 to the minus fourth. Still, it's weak. And we know that because it's weak, the NO2 that you see here, this NO2 will then have to react with water and try to form its parent. All right. So the water is sitting there, and it can donate this nitrogen sitting here, it can try to get that proton away from that water and form HNO2, which will be aqueous because it's in water, and creating an OH minus for us. So what we see is this thing which we called in the previous video a basic salt because it had a parent that was strong, a base parent that was strong, and a weak acid parent. We now see why it's called a base, because it produces OH minus, and that's the original Arrhenius definition of a base, something that increases the OH minus concentration, the hydroxide ion concentration in solution. So one of the keys for you to succeed in this ionic equilibria is to be able to write the proper equilibrium. And these hydrolysis equilibrium are hard to identify. And it takes practice, just doing one after the other until you can identify how things are going to break apart into its individual ions. And then you can write the proper equilibrium for your problem. I hope this helps you out, and good luck.